Bismillahirrahmanirrahim. Wassalatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Okay, so today this is the second lecture on recursion. So yesterday we talked about the main concept of recursion and also the computational thinking process on how to solve a recursion problem, which basically use from trying to identify the pattern, okay, the pattern that repeats, okay, that should repeat in a recursive manner, identify the base case, which is the stopping condition, which is very important to make the program stop at some point in time and not going for endless loop, okay, and also the recursive case, which is actually the algorithm for the pattern that will be recursively repeated. So you need to do later on the algorithm and finally jump into the programming implementation. So today we're going to talk about also a very important example in introducing recursion, which is called the Fibonacci series. Okay, so Fibonacci series usually it's represented by the population growth of rabbit colony. And I remember when I was a student, I got an exam on this, and I don't forget it because it was a little bit tricky. But now when you understand the way on how to solve it, it's not difficult, but you must understand first the problem in a proper way. So imagine that you have two rabbits, okay, and these rabbits are going to reproduce every month. Every pair of rabbit, they are going to bring another pair of rabbit every month. Okay, so for example, if I say after 12 months, how many rabbits you will have? How many rabbit pair you will have? Okay, so this is the question. Okay, so now you have one. After 1 month, you will have another one, so two. Then these two are going to produce two more. And these four are going to produce four more. And this, okay, every pair is going to produce another pair. Okay, so the colony begins with a single pair, and after 1 month, they are going to reproduce, and so on. So here, our input, we need to understand what will be our input, what will be our output. So now, for this problem, the input will be after n, which is the number of months. After 24 months, what will be the expectation of the number of rabbits that will be reproduced? Okay, and the output will be just the total number that you would like to have. Okay, so for example, if I put 5 months, after 5 months, we're going to have 8 pairs of rabbit. Okay. So this is the mathematical description of the problem, but I'm going just to consider this one. So same thing, we're going to follow the computational thinking process, which is decomposing the problem into sub-problems, finding the pattern, defining the algorithm and the abstraction. So here, okay, so look, in generation one, now break down the problem into smaller pieces, understanding the reproduction style and recognizing the pattern. So usually what you can do, how you can implement this decomposition and pattern recognition. You can draw, for example, now I'm going to draw it. Let's say in the first generation, I'm going to have one pair, which is the starting. Now in the second generation, this pair is going to reproduce another one. So usually now, when you want to do the first step, the second step, you need to draw something similar. Now I did it in this way, maybe you have another way, but you need to try to identify what will be the pattern. Okay, no, in generation 3, how many we will have? So this one is going to give one pair, and this one is going to give another pair. And in generation 4, okay, so every pair will be giving another pair. So what is the relation here? Okay, now it's if we consider the next generation, what will be the number?
8. After this, generation 4?
Yeah.
8 pairs.
Yeah, I know, but how are we going to compute it? Now we need to find an equation. Usually you will implement this into a program. So what will be the equation here?
2 to the power of n. Well, n
No.
is generation n. Yeah.
No. Actually now, for example, in generation 3, I'm going to have the number of generation 1 plus the number of generation 2. In generation 4, I'm going to have the number generation 3 plus generation 2. Okay, so here 2 plus 2, I'm going to have 4. Okay, so basically here, the number of rabbits in the next step will be the sum of the 2 previous steps. Okay, so this is the relation. Now, if you make the exponential that you've made, you'll not find it correct, because for example, 2 at the power of 4 it's 16, and here you have 8.
Minus 1 and minus 1.
No, if you make for 5, 6, maybe we need to elaborate more. It's not going to match. You can try it. You can try it. Okay, so each pair of rabbit contributes to an increase of population following a specific pattern, which is this one. Okay, after the first pattern, the new pair, okay, the number of new pair is the sum of the new pairs from the previous 2 months. Okay, the number of pairs here is the sum of the previous 2 months. Now here, the number of pair here is the sum of the previous 2 months also. Okay, so it's the previous 2 months, so maybe I made one, this one is not part. Just a moment. Yeah. The sum of the previous 2 months. Yeah. I removed one. Yeah, the previous 2 months. Okay, now I only remove this one. Okay. Look now, the previous 2 months, Gen 4, Gen 3 plus Gen 2 is equal 3. Okay, this is the relation. Okay, it's the sum of the previous 2 months based on the pattern here, identifying the new pattern. So understanding single reproduction cycle by the pair. So yeah, this is the reproduction, how it works. Let me just read it again. So every month, every mature pair of rabbits produces a new pair of baby rabbits that will mature and reproduce starting from the following month.
So it multiplies. So every year it multiplies.
Multiplies, yes, but following this pattern here. Okay, so the number of rabbits into, for example, generation 4 will be the sum of generation 3 and generation 2 will be 3. And so on, it will repeat. So next time, it will be the sum of generation 3 and 4, which is 3 plus 2 here. Yeah. So basically, after doing this analysis, we need to find the algorithm. Okay, so this is how it works. For example, at F2 is equal to F1 plus F0. F3 is equal to F2 plus F1. Okay, we take the whole sum. And F4 is equal to F3 plus F2. And so on. Okay, so this is the relation. So here we can identify that we have Fn is equal to Fn minus 1 plus Fn minus 2. And this is the pattern that we look for. Okay? So what is the base case here? What is the base case? We start by n equals 0 and n equal 1. We cannot make the sum only if we have 2 values. Okay? So we start, the recurrent case start by f equal 2. F of 2. F1 plus F0. So this is the base case. Okay, it must contain 2 numbers. And the recursive case is for n greater than 1, starting from 2. Okay, we will have the number of rabbit n is equal to rabbit n minus 1 plus the rabbit n minus 2. Okay, so this will give us the following algorithm. Now we go to the step to the algorithm. Okay, here in the algorithm we define the name. Okay, calculate the rabbit pairs using Fibonacci sequence. The input will be n, the number of months, and the output will be an integer representing the number of rabbit pairs after n months. So this is the start. We define a function, and the base case contains n equal to 0 and n equal to 1. So we define them here. And finally, if n is different from 0 and 1, it will be the sum of rabbit n minus 1 and rabbit n minus 2. That's the algorithm. And this algorithm now, we can translate it to Java. Okay?
Can we go to the pseudocode?
Yes. So the pseudocode is going to be just an implementation of this formula. Okay, a representation of this formula as steps. So the pseudocode, you will write the steps just in plain English, but of course there is a certain way on how to write it. I mean, you start by algorithm, you start by identifying your input, you start by identifying your output, and then the steps to follow. This is how we write a standard algorithm.
Doctor, why do we need the sum of both rabbit pairs n minus 1 and n minus 2?
Yeah, this is the pattern of the Fibonacci series. Okay, based on the description here. Okay, this is the, based on the description. Now, let's take an example here. This is the sequence of Fibonacci sequence. You start by 0 and 1, then you make the sum of the two previous, it's 1, the sum of the two previous is 2, the sum of the two previous 2 plus 1, 3, and so on. This represents the same pattern as here. Yeah, it's not obvious to identify the pattern just from this description. But for example, if I present a problem like this as a Fibonacci sequence, it will be easy. Now, I can give you this sequence. Now, imagine I give you this sequence and say implement this. Okay, forget about the rapid reproduction. You have this sequence now. Okay? So this sequence, what's the pattern from this sequence? Okay, forget about the rabbit. Now, I give you this sequence. This is how the rabbit are going to be reproduced. But you have this sequence.
It's the sum of the first two numbers.
So this number is what? Is the sum
first two
of this one plus this one. And now this number is the sum of this one plus this one. Now it's easy to see it like this. Okay? And basically what we made here, it's just another way of representing this pattern. Okay?
I get it.
That's the way. Now every pair, so we have here, for example, at this stage we have 3 pairs. They're going to produce 3 pairs. Okay? And that's it. Okay, now if you have this sequence, is it clear for the algorithm?
Yes.
Okay, now in order to calculate this sequence, you need to start from 0 and 1. That's the base case. Okay, the base case, it's not necessarily only one value. It can be, you may need 2 values, 3 values, depending on from where you start. Okay, and then you identify the pattern and the relation. Now, Fibonacci of n, the recursive case, will be the Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay, which give us this formula. And finally, we will have the following algorithm. Okay, we start by the base case, n equal to 0, n equal to 1. And if the recursive case, we are going to calculate, return the sum of 2. Now, look at this in Java. Okay, are you able to see my screen?
Yes.
Or should I make it like this? Better? Okay, so you have here the rabbit pairs. We start the base case n equal to 0, we return 0. If n equal to 1, we return 1. And then return rabbit pairs n minus 1 plus rabbit pairs n minus 2. So it's going to keep going back until it reaches 0 and 1. So at some point, and then it will roll back and calculating the sum. واضح؟ Okay, so we can try it. Look now, the same algorithm, you can implement it in Java, you can implement it in Python, okay? You can implement it in C++. So I want to tell you, programming is just a means to represent an algorithm. But the most important thing in recursion now, well, in what you've done in CS101, is finding the algorithm first. Okay? So never jump into coding unless you find the correct steps on how to solve particular problem. And this is a test function. Now, I can go to NetBeans to show you the code in action. I will give you the code later on. So, rapid population here. Okay, so this is the code. Now, the number of number of months equal to 5. Here we are going to call rapid pairs. And rapid pairs is a recursive function. So it takes n, which is the number of months, and later on it will return the value. So let's try some values. So after 5 months, there are 5 pairs of rabbit. Let's try 0 now, the edge case. After 0 months, there are 0 pairs of rabbit. We can try with 1. There is 1 pair. We can try, for example, with after 10 months, 55 pairs, and so on. Okay, here I've made a Fibonacci test, okay, which identifies. So these are the test cases. These are, for example, the month, and here we find the real value. Now what we will do, we can calculate the expected value, which is here. This is what we expect, and this is the actual that will be calculated. And of course, we need to have equality between the expected and the calculated to make sure that it is correct. Okay, so it will pass. It passes all the tests.
So doctor, back to the rabbit pairs.
Mm-hmm.
Back to the rabbit pairs. I don't understand the logic in our code. If n equal 0.
If n equal to 0, it will just return 0.
Okay, yeah, I get that.
Okay.
I wrote 1.
So
Because we can have a minimum of 2 months for the
yeah, let's make
right?
a tracing here. So what will happen? So if n equal to 5, let's make it step by step. If n equal to 5, okay, what it will return? It will make return f4 plus f3. صح ولا؟
Yes.
Do we know f4 and f3?
No.
We don't know. Okay, so it will make, we will calculate for n equal to 4, we need to calculate f4. Okay, so for f4 equal f3 plus f2. And we need to calculate for 3 because we don't know also f3. We need to calculate equal to 3. We need to calculate f3, which is equal to f what? f2 plus f1. So what values do we know? So initially we know which values. We know f0 equal to 0 and f1 equal to 1. These are the two values that we know, okay, which are here. واضح? Okay, so now f1 we know it. We can replace this by 1, but still we don't know f2. So I'm going to calculate now n equal 2. F2 equal to F1 plus F0. So here F2 will be equal to 0 or 1 plus 0 equal to 1. Now, since we calculated F2, we are able to say now F3 is equal to 1 plus 1 equal to 2. Now I am able to calculate F4, which is equal to 2 plus 1 equal to 3. And finally, I am able to calculate F5, which is F4 plus F3. F4 is 3 plus 2 equal to 5. This is how it will work in the memory stack, because there will be a stack of memory. You will learn this in operating system, how this is going to be stacked into the memory until it reaches the base case. Then when it finds the values for, look, all of these values will be waiting in the memory until they are calculated. Okay? Until they are calculated, and finally, when we can calculate a certain value, like for example F2, it will help calculating a pending value, which is F3. واضح? So this is based on the concept of memory stack. I will try to write you something that will explain this process. Okay, you can read it. But of course, don't worry if you don't understand this deeply. It's based on the concept that you'll learn later on the operating system. The way on how the information is stored in the memory and later on retrieved during computation. Okay, it will go to assembly code and will put, so all these values will be in instance waiting until calculating other values. And we've done something similar with the factorial, if you remember. Okay, so I want to calculate factorial of 5. It depends on factorial of 4, it's not known. It depends on factorial of 3, it's not known. Depends on factorial of 2, it's not known. Factorial of 1, now it's known. Now, if I know the factorial of 1, I will calculate factorial of 2 because it's 2 multiplied by 1. And then I will calculate factorial of 3, then calculate factorial of 4, and finally calculate the factorial of 5. So it will goes to the bottom of the stack and then will goes up, roll back until it calculates all the pending computations. So some of the computation will be pending until I reach the base case. And this is why we need to have the base case. If you don't have base case, it will just going down, down, down until the memory becomes full and we'll have stack overflow and the program will crash. But once it finds the base case values that it needs to do the computation, it's going to roll back and do the computations in the other direction. Okay, until finally returning the correct value. So as you have unknowns, it will just continue going down. When all the unknowns becomes known, so it will roll back to calculate all pending unknown values until it reaches the recursive case, the initial recursive case. Okay. Is it clearer? Okay. So this is why I try to introduce for you several cases. Okay, are you familiar with this function? Everybody hates math. Who likes the math? Only one. Yeah. Not surprising. Yeah, math is enjoyable because people don't like math. It's because they have issues in understanding these notations. But if you understand the notations and are clear to the mind, this is why I like engineering, because engineering, it maps the abstract math to real world problems. So at some point in time, you'll understand that all these expression makes a lot of sense in reality. But when you just see them like this, it makes a little bit of trouble. But anyway, so forget about these ones. So the exponential, everybody knows the exponential and the logarithmic function. Okay, so the exponential, imagine that you would like now how exponential is calculated by a computer. It's not based on simple mathematical operation 1 plus 1 or something. It's just a function, a complex function, like logarithmic also. So usually to calculate these values, or we approximate the value, we can make what we call Taylor expansion. Have you seen this Taylor expansion in some of the math courses? Okay. So Taylor expansion, it's based on the concept of derivative. I think everybody knows derivative. Okay, and in some of the ways we can express a function like this as a sum of values based on certain number of iterations and based on the x. For example, I want the value of ex. It will be the sum of x at the power of 0 divided by 0 factorial plus x at the power of 1 divided by 1 factorial plus x at the power of 2 divided by 2 factorial and so on. Of course, there is complete mathematical proof about this. This is related to mathematicians. We don't care about it. Now, we are computer scientists. We have this equation, and we want to develop a program that is able to approximate the value of the exponential. Okay, your colleague is a mathematician, tell you, okay, now I have a proof, this works, so provide me a way on how to find the value on a calculator or, for example, on a computer program. Now, this is our role. How can we do that?
Recursion.
أول حاجة الآن we need to identify, is there any pattern?
Yeah.
Okay. Okay, consider this as an observation problem. Forget about the math.
For every
Okay. What pattern is recurrent here?
The exponent is the same as
when the exponent is
Yeah, look.
so the factorial.
For example, if n equals 0, I have x0 divided by 0 factorial.
One.
If n equal to 1, I have x1 divided by 1 factorial. If n equal to 2, I have x power 2 factorial. So there is a pattern, صح ولا لا؟
Yes.
below n equal to 10, x power 10 divided by 10 factorial. If it is 100, same thing, x power 100. So you can know what's going to happen after 1,000 iterations or 2,000 iterations. Now this is the pattern. This is even easier than the previous example. Now we find the pattern here. And at the end, it can be it's a sum until infinity of xn divided by n factorial. I can do this for 1,000 times, 1 million times, 1 billion times, sum. Okay? And every time the factorial is going to grow and the value is going to be very small. Factorial of 100 is going to be very, when you divide by a very big value, you know, you will find 0.99 zeros and something else later on. So we can stop, we can have a good approximation after 10 iterations, 20 iterations, depending on how big the stack is that is able to do the computations. واضح المثال ولا لا؟ Okay. So assuming this formula, now we would like to implement, we can do a recursive program. خليني قبل ما أوريكم الحل. Okay, let's think on how we can do it. What's the base case here? Now you need to find pattern. وجدنا الباترن. Now I need to find the base case, the recursive case.
Base case n equals
n
1.
equal
1.
والزيرو ايش تعمل لها؟
0 I mean, 0.
أسهل شيء n equal to 0.
Yeah.
n equal to 0, what will be the value?
1.
1. 0, x power 0 is 1, divided by 0 factorial is 1. صح ولا لا؟ What is the recursive case? Okay, what we are looking for.
We're doing the summation, doctor.
شوف ما هو الكتابة جيدة. Okay. Okay. What is our function? أول حاجة احنا we will calculate the function f. صح ولا لا؟ It's a function. We're going to calculate a function f. F depend on what? Depend on what f?
On
On x. وعلى ماذا أيضا؟ وان صح ولا لا؟ اكس هذه اتس جيفن ان هي مش تتغير عندنا. اف اكس ان تساوي ماذا؟
1 in count and 0.
اوكي ناو اف اكس 0 تساوي 1 صح ولا لا؟ اوكي ناو اف اكس 1 تساوي ماذا؟ تساوي 1 بلس
x to the power 1
اس 1 بلس 1 هذه 1 وهذه اكس باور 1 وات؟ x باور 1 x divided by 1 factorial 1 x divided by 1 يساوي x صح ولا لا؟ I can write this as f x sorry f x 0 plus x صح ولا لا؟ الطلاسم بدأت توضح الآن. علاش قلنا الكتابة تفرق، تقعد تفكر فيها تضيع. You need to write down. You need to write down things. Okay. Now I want to calculate the next one.
it's going to be
Forget about this. أعطيني الكالكوليشن.
f
تساوي هذه 1 هذه x وهذه what؟
it's going to be
x2
x of 2
x2 okay divided by factorial of 2 is equal to, so I can take all of this as this one صح ولا لا؟ plus the new term إذا ما وضحتش نزيدوا الإكس 3 which is equal all of this plus x power of 3 divided by 3 multiplied by 2 6 and we can write this as 2 3 and 3 صح ولا لا؟ Now I think it's sufficient.
yes please
Last step.
Okay, so now if I give you fxn
it's going to be f(x1)
fx what؟
f(x1)
لا عاد
plus
منين جبت ال1؟ n minus 1
1 plus x is always repeated so it's just f of x of 1
شوف لي هذا الآن fx3 تساوي ماذا؟ fx2 هذا الباترن صح ولا لا؟ شوف fx2 is equal to fx1 plus so fx minus 1 plus an additional term. What is this term? x power n
over n factor
n factorial.
that's the recursive
حلينا المشكلة. هذا recursive case الآن. واضح؟ So this is how you need to think. It's not easy in the beginning. لكن okay now of course I give you 4 different problems. But now if I give you, for example, in the assignment you will have instead of exponential logarithmic, which is Taylor expansion. You have an equation like this. You'll do the same thing to find. Yeah.
اخر شيء 3 بيكسين 3 صح؟
Yes.
ولا 3 بيكسين؟
No, 3 factorial. 3 factorial here and 2 factorial here.
لا في 3 over there
Here?
yeah
Yeah, 6. 3 factorial is 6.
So we don't put 6 here.
No problem. And I calculated.
I mean the other side.
No problem. This is just to keep the pattern.
Okay.
No problem. You can write it anything. But for me to keep the pattern easier. Okay? So that's pretty much about it. Okay? Now, this is the description of the problem. This is the how to find the pattern. You know, you can find here the description of the pattern here. Okay? And now, this is the algorithm. Of course, here we have 2 recursive functions. For recursive function exponential, you have also to define the factorial that we did before. We can use it the same. You need to define also a factorial. Okay? And then this is the algorithm, very simple. Base case, if n equal to 0, then return 1. صح ولا لا؟ Okay? else return function x n minus 1 plus this term, power xn divided by factorial of n. We can use math.power, okay, because now this is algorithm. We don't have math, but in Java, when we make it in Java, it's simpler, okay. You have here exponential Taylor. If n equal to 0, return 1. Otherwise, return Taylor series xn minus 1 plus math.power xn divided by factorial of n. And factorial, this is the same function, recursive function that we have done yesterday. Okay? So this is simple. Like, what is more complicated is what we have done here. Okay? Now you have an exercise very similar to this one, which you can find on exam GPT. Okay? You have the expression of the logarithmic. And do the same thing, base case, recursion, pattern, algorithm, Java. So try to apply this one, and tomorrow share with me what were your problems. So I will do the grading by tonight, so try to finish this by tonight, and tomorrow we can discuss if you face any difficulty. Okay? Okay, that's fine.